So this is the second respiratory session. This is on diffusion or perfusion limited gas transfer. Again, the format, all these talks are in sequence. There's a bit of knowledge built up in between them. We'll go through the questions and how they can be asked, some background knowledge, and then we'll go through a model answer. The questions that you'll find asked on this will relate mainly to the first steps in movement of gas across membranes, and then an understanding of where that gas goes once it's in the bloodstream. And they all relate. So we'll build our knowledge on that, and you should be able to answer this type of question: diffusion limited gases, the carbon dioxide, oxygen, hemoglobin dissociation curves, and everything that's derived from them. One example is to be asked to explain Fick's law of diffusion. You can be asked about Henry's law and how it relates to partial pressures of gas. You can be asked about diffusion constants. You can be asked what is the difference between diffusion limitation and perfusion limitation in a gas. The textbooks are full of these. West is particularly good in the technical aspects. If you look at Guyton, it's a very good overview and puts everything in context well. So there is some assumed knowledge here, and that you understand what a gas is, you understand what a liquid is, and the interface between the two that performs a layer or a barrier type function, and how gases move into that medium. So what we're concerned with is Fick's law of diffusion, first of all, and we'll try and step through that in a logical way that is very intuitive. Everyone should know this. We talk about a membrane in Fick's law of diffusion, and the general aspect talks about a membrane. What we are going to be concerned with when it comes to answering respiratory questions is the alveolar capillary membrane. So right down at the base of the lung, at the point at which gas exchange occurs. If we talk about a membrane, for argument's sake, I'm going to draw it like West does, and say that we have a membrane that has dimensions of area, of thickness, and several properties associated with it that we'll go through. This is going to be a membrane that consists of one layer of an alveolus, a basement membrane, and one layer of a capillary. The net effect here will be exactly the same. We have a substance on this side, a gas, and we want it to go from this side through and come out the other side, i.e. process of diffusion. It runs down its concentration gradient. So the concentration on this side, or P1, is higher than the concentration on this side, or P2. That is one factor that determines the rate at which this thing diffuses across the membrane. If we have lots on this side and none on that side, then there's a pressure gradient for it to move across. It's pretty logical. If we talk about the amount of the substance that can diffuse, we'll also talk about the larger the surface area available, then the larger amount is able to go across. So it's related to the surface area. The other thing we'll talk about is the thickness, or how far this substance interacts with the membrane, how much interference from one side to the other that exists. So the thicker the membrane, the slower the diffusion. So Fick's law relates all these things into an equation. And the volume, or the amount, or the partial pressure difference, or the diffusion rate of this substance is related to the surface area. It's proportional to the surface area, such that the higher the surface area, the more diffusion occurs. It's also related to or proportional to the pressure gradient, or the difference between P1 and P2, higher pressure to lower pressure. The larger the gradient, the larger the diffusion. And it's also related to the properties of this membrane, in that this membrane has a charge, it has a pore size, and it has a solubility associated with it. So we talk about the properties of the membrane itself, i.e. this thing called its diffusion capacity or its diffusion constant, and we'll come back to that. But also the thickness of the membrane. The thicker the membrane, the less diffusion occurs, i.e. it's inversely proportional. So Fick's law associates diffusion, or rate of diffusion, to surface area, pressure gradient, diffusivity, or the constant, and thickness. That all should be pretty intuitive. What we're going to do now is add to that the lung and a few types of gases that we know of. And the lung has fixed properties that weigh into this diffusivity. Likewise, the gases have different properties as well. So the diffusivity itself is proportional to the solubility of the substance in the membrane. And we'll talk about that when we talk about oxygen and we talk about carbon dioxide. Carbon dioxide is very soluble in lipid membranes. So its diffusivity or its solubility is very high. Solubility is high, diffusivity is high. Oxygen does a pretty good job, but not nearly the job that carbon dioxide does. It's not as good. So it doesn't have as near a solubility as carbon dioxide. And the other thing that matters is the temperature. So we are concerned about the temperature. It has properties that give kinetic energy to molecules. And we're also concerned with the size of the molecules. What I'm after here is the size of the molecules. Temperature in the wrong spot. And we're concerned about the size of the molecules, i.e. the bigger a molecule, the harder it's going to be to get through any given membrane. And it happens to be a square root. That's how the maths turns out. So Fick's law relates rate of diffusion, surface area, pressure gradient, diffusivity, and thickness. Diffusivity is a property exhibited by molecules within the membrane, differs various membranes and molecules related to molecular weights, solubilities, and temperatures, or kinetic energy involved. Now we want to relate this back to the blood. So I'm going to put up a model here, and we'll build on that throughout these talks. What we're going to do, we'll get rid of that bit. And consider a lung. And a lung is very stylised. Comes down to an alveolus, and we can exchange gas into the top of this lung. And then what we have is the thin membrane of a blood vessel approaching the exchange surface of the lung. And what we're going to talk about now is the ability of a substance to start in here and end up in here. It will do that down a pressure gradient, such that if there's lots of molecules in here, the concentration is higher in here, lower in here, and this substance will move according to the diffusivity of this membrane, the amount of it that goes through according to the surface area, pressure gradient, and diffusivity. Obviously, the thicker this membrane, the less diffusion we have. For example, if you have COPD, you can't exchange oxygen as well. Your membranes are So if you have interstitial lung disease, your membranes are thicker. You can't exchange oxygen as well. So what we're going to imagine now is we clamp ventilation such that we keep concentrations normal here, and we clamp circulation such that everything will equilibrate. And what we're going to find is that the particles on this side will equilibrate, moving into here, such that we're going to have roughly equal numbers on this side of the membrane, equal numbers on this side of the membrane. What will happen then is there's no pressure gradient and therefore no diffusion. So despite the surface area, despite diffusivity, despite the thickness, equilibration can still occur and there'll be no diffusion because pressure gradient doesn't exist. Now I mention that because if the goal is to get oxygen from here into here and we have stasis of blood flow, this will prevent oxygen from moving. It'll move and then it won't be replaced, i.e. that oxygen can't be picked up from the alveolus, and if there's no distribution of that oxygen, that's a bad state to be in. This will become important when we talk about mismatch. So let's reference this diagram now for later. What we're now going to do is, after equilibration's occurred, allow replacement of this substance again. We'll put some more in here. And then we'll allow the circulation to flow, such that these molecules are now transported away. And these ones no longer exist. And we end up with a situation where pressure gradient exists again. So these substances will move down the pressure gradient. And once that pressure gradient returns to zero, at that surface, the substance won't diffuse any further. So when the pressure gradient is zero, doesn't matter what the surface area is, doesn't matter what diffusivity is, doesn't matter what thickness is, nothing moves. So what we are trying to determine here is across an alveolar membrane into the circulation is that for a given lung, the surface area remains relatively constant at any one point in time. The thickness remains constant at any one point in time. The diffusivity or the properties of the membrane and the gases that we're looking at remain relatively constant at any one point in time. So for a given respiratory unit, for a given lung, at any one point in time, the thing that determines diffusion is going to be pressure gradient. So now the big point comes that if we want to facilitate oxygen moving into the bloodstream or carbon dioxide moving out, we need to maintain the pressure gradient. So to maintain the pressure gradient, we have to supply oxygen and we have to remove CO2 from the alveolus, i.e. ventilation. If we ventilate, we circulate these things. We'll come to that a little. Likewise, if we keep delivering CO2, we will allow movement of CO2 along its concentration gradient. And if it's removed from here, it'll continue to move from the blood. If it's not removed from here, it won't be removed from the blood. It flows down its concentration gradient. So if we can't remove it from here, i.e. we don't have enough ventilation, CO2 builds up and stays in the blood. It doesn't have a concentration gradient to move across. And that's the basis of hypoventilation causing hypercarbia. Same rules apply for oxygen. If we ventilate the oxygen, we keep increasing its concentration here, it will flow into the blood until it equilibrates. I.e., there's a lot of oxygenated blood sitting in the lungs in someone with a cardiac arrest. It doesn't go elsewhere is the problem. So if we produce a circulation and remove that oxygen, then we maintain a concentration gradient for more oxygen to be offloaded into the capillaries. So we've got principles of gas movement, and we say that they rely on diffusion through Fick's law, and it's mostly related to the pressure gradient if we talk about a given lung at a given point in time. So using that information now, we can talk about how much of a substance moves into the blood. And when we start talking about that, we talk about the limiters to that occurring. When we talk about the limiters to that occurring, we can talk about concentration gradient being the limiter and the rate at which the concentration gradient is renewed. So for a substance like, we will choose carbon monoxide is the one that everyone knows. We'll choose carbon monoxide in this example and say that carbon monoxide that ends up in here diffuses across the membrane and ends up in the blood, such that there is carbon monoxide here. If we clamp and clamp, we say that the concentrations will equilibrate. This gas has to move across the alveolar membranes, and there'll be no more flow when there's no more pressure gradient. That'll occur quite quickly. What we also know, though, is that carbon monoxide in the blood is pulled out of the substance of the blood. It's packaged up into red cells, such that the plasma that's in contact with the membrane rapidly returns to zero concentration, or near zero concentration. So carbon monoxide has the unique feature of being able to maintain a concentration gradient, or a pressure gradient. What we're now going to do is talk about the situation where we unclamp the circulation, and that'll allow several things to happen. Carbon monoxide will be pulled away from the respiratory membrane and allow a pressure gradient to exist again. And so carbon monoxide will continue to travel in. Likewise, more hemoglobin will be delivered, and it won't have carbon monoxide on it yet. And carbon monoxide will be consumed, maintaining a pressure gradient, and allow more carbon monoxide. So we end up with a situation where the amount of carbon monoxide that can get into the circulation is not limited except for its ability to diffuse across the membrane. The only limitation on moving carbon monoxide is the membrane itself, the diffusivity of the membrane. Because when carbon monoxide makes it into the circulation here, this will move in, bound up by hemoglobin. Straight away, it maintains the concentration gradient. Likewise, more circulation will provide more hemoglobin and provide more substrate to mop up the carbon monoxide. So the perfusion here is not a limiter. This movement is limited by diffusion. So this is an example of a diffusion-limited gas. Let's now talk about something like nitrous oxide, the same thing that we use to put kids to sleep. I'm going to just develop our diagram here again. This is a common one that we'll keep coming back to. So, blood vessel across an alveolus at a respiratory membrane has a flow, and we're going to talk about nitrous. Entering into the alveolus, forming a concentration, it'll have a concentration gradient down which it moves. Now, nitrous is very soluble. It moves across membranes very well. It maintains a low volume of distribution, if you like. It stays in the aqueous solution in a very small amount, so it has a high partial pressure. It will move into the circulation, and if we stagnate this circulation, very quickly increase its concentration. It moves so readily. Increases concentration very rapidly, actually, such that the equilibration of partial pressures on either side of our respiratory membrane occurs very rapidly. The movement across this membrane is not the limiter in that case. It's the pressure gradient, the concentration gradient. What we're now going to do is again open the circulation such that this nitrous is moved away from the exchange surface and more is allowed to move in. Very quickly it equilibrates. New blood moves in, again the nitrous is taken away and more moves very quickly. It crosses the membrane really well. So the limitation on how much nitrous goes through the system and into the blood is purely associated with the perfusion of the lung. The limitation here is the perfusion, not the membrane itself. So this is a good example of a perfusion limited gas. So what we end up with is a situation of contrast between carbon monoxide and nitrous. And it's to do with the properties of the gases, their interaction with membranes, and their ability to equilibrate to get the same pressure gradient on either side of the membrane, and how quickly that occurs. Nitrous, for the reason that it crosses the membrane very quickly, it's light and it is very soluble, equilibrates rapidly in the blood, and more blood passing through is the thing that loads it from external into the blood. It's the limiter. So more blood means more nitrous in the system. Doesn't matter how much more you put in here, how much more permeable you make that membrane, the limitation here, it moves so readily, so quickly, that blood flow is the only thing that limits how much goes in. And that's perfusion limitation. Carbon monoxide, on the other hand, is pulled out of the blood onto hemoglobin very rapidly. And so the concentration effectively in here falls rapidly. So there's a gradient maintained. And despite perfusion, you can slow perfusion down. And this gradient is maintained because of the properties of carbon monoxide in the blood and across the membrane. It's not as diffusible. So we end up with a situation where the limitation here is the membrane itself. It's the only thing stopping, or the only resistance to loading carbon monoxide into the blood. Now that's a different argument to how much of this substance can exist in the blood. We'll come to that when we talk about oxygen and carbon dioxide hemoglobin association curves. That's a separate question. What we're talking about here is the ability to move. And so eventually the amount that ends up in the circulation is related to limitation at the membrane or limitation by perfusion. So when we talk about diffusion, perfusion, limited gases, we can take this concept and now start to draw some curves. In the end, these will be the curves that you use in your exam. You'll be asked about Fick's law. Reason it out. Very simple. Now what we're going to talk about is a curve of time, and this is the time that red cell or blood flows through an alveolus. So it starts here at time 0 and it takes under a second for this to occur. So we have a time axis here at 0 and out to about 1 second. And what we're going to measure is the partial pressure of the gas. And we can measure it arterially, we can measure it at the other side of the lung. And when we talk about this process, this all occurs very rapidly. And in a normal lung, you don't usually know the difference. Pathological lung, it's very different. If we talk about nitrous, we say that on the way through the capillary, the blood saturates very quickly. It can't hold any more of this gas. So the partial pressure of the gas reaches a peak. So that will be nitrous on this curve. So it doesn't get too far through the capillary, and we've already saturated. Carbon monoxide, on the other hand, looks more like this in comparison. It's a flatter line. And what that says is the amount of saturation of the blood with carbon monoxide occurs much more slowly. It still reaches the peak, it still becomes saturated, but it's much slower. It's a much slower process. So this is limited by properties of the membrane. This is diffusion limited. This is unlimited by the properties of the membrane, and it is limited by how much blood you can push through. So this is perfusion limited. And that's nitrous and carbon dioxide. Now, this becomes important because we run on oxygen, not nitrous. If we add oxygen, it looks like this. This is the oxygen curve. Characteristics of perfusion limitation. However, if we have a diseased lung with a thickened membrane, we end up in a situation where oxygen, because of its properties of solubility, its molecular weight, and its interactions with the membrane, that looks like this. And it may or may not attain this value. If it doesn't, we end up with a situation where the blood is unable to be loaded with enough oxygen, i.e. the membrane is causing limitation. The membrane causes diffusion limitation of oxygen, and that is a pathological problem. That's not survivable. So these are diseased lungs. So that's the difference between perfusion and diffusion limited gases and how it relates to what we see. Now, the questions that will be asked, we'll answer one for you now. Explain Fick's law of diffusion. Fick's law of diffusion relates the rate of diffusion to a membrane's properties and a gas's properties. The higher the surface area of the membrane, the larger the pressure gradient, and the larger the diffusivity, the higher the diffusion rate. Likewise, the thickness of the membrane is inversely proportional in that the thicker the membrane, the smaller the diffusion. The prompt in this question is what factors determine the diffusion constant or diffusivity. Diffusivity itself is a property of the membrane itself and the interactions of the molecule and the membrane, such that the larger the molecule or molecular weight, the slower the substance moves across the membrane. Likewise, the more soluble the gas or the substance in the membrane, the quicker it moves across. And that's factors relating to diffusivity. What's the difference between a diffusion limited and perfusion limited gas? Diffusion and perfusion limited gases can be easily defined on a volume, on a curve that relates the partial pressure of the gas to transit through the capillary membranes. A diffusion limited gas can be thought of as carbon monoxide, in that the amount of carbon monoxide that is loaded into the blood is limited by its movement across the respiratory membranes, and that's related to factors in Fick's law. And a perfusion limited gas, such as nitric oxide, has this relationship in the capillary membrane, such that a lot of this gas is loaded rapidly. Its rate is related to the pressure gradient that it sees, not the membrane resistance of the membrane that it sees.